Okay, here we are with the PowerPoint. It says material testing, but specifically we're talking about stress and strain curves. And there's two kind of testing you can do. We know that static means things that are not moving, so here we're talking about a constant load, like just setting a weight on top of something. Dynamic is when things are moving or changing, so here we're talking about loading where we maybe put the load on, then we take it off, and back and forth. We're specifically interested in static material testing, and these are the items that we're going to look for. And these are the kind of tests we could have. Uniaxial testing means that we're just testing in one straight line. It's the easiest testing to do. For instance, in this machine right here, we would attach one piece here, and then this bottom arm would move down and pull on the piece. Here, this is a smaller version of the same thing. Our standard test pieces look like this, and it's called a dog bone shape. And basically it's narrowed down in the middle so that we're sure the break will occur in the middle. That way we're sure of the cross section we're using. If we use this end would be attached into a clamp, and this end would be attached into a clamp, and it very likely might break at one of these points, which would not give us good test data. Here you can see that same dog bone shape has been attached at each end. This is how it's tested. This is our standard stress strain graph, and I've given you a copy of this. You should put this in your notebook, and as you go through this video, you should make notes on your graph I gave you. Here they're graphing force versus elongation. But if I have two different sizes of test material here, but they're both the same material, I should get the same test results for both of them. However, this one would seem much stronger than this one just because it's bigger. So it would give us good data on just the material itself. So we take it and we adjust for the size of the test sample we're dealing with. So instead of graphing force, we actually take the force and divide by the cross-sectional area. Notice this is the cross-sectional area to get a new variable called stress. And this is a lowercase sigma. And you should copy this formula down for your formulas. Stress equals force over area. So this is how it would work. If I put a 430-pound force on this shape, and I've got a cross-sectional area here with a diameter of 0.125. It's a circle, so I'd use pi r squared to find that. I divide here and I get a PSI, pounds per square inch, for my stress. It's the same thing on the length. I wouldn't want to just say how long is it, because it actually depends on how long it was to begin with. This is a delta. It's a lowercase delta, and that's what we use for elongation. That's how much it changes length. And then this is the initial length. This is an epsilon, and we use epsilon for strain. So this is the second formula you should write down on your formulas. And a problem would look like this. If I have an initial length of 3, and it changes length by this much, it gets this much longer, I divide those to get the strain. Notice inches over inches cancels out, giving that strain either has no units, or we might write it inches per inch. So this is what your graph is labeled as, stress and strain. The initial part of it is linear. This is the elastic range. This is the range where if I just put this much stress on it and then I let the stress off, it'll go right back to the same shape. Think of the elastic range like a rubber band. It's where if I stretch it, it goes right back to the same shape. And right here is the proportional limit. It's at the end of the linear part. This is the point at which if I stress less than this, it's going to go back to its initial shape. Anything past this, it's going to deform and it won't go back. The modulus of elasticity, E, is the proportional constant. basically, it's stress over strain. That's rise over run. That should sound familiar. That's the slope of this portion. Gives us the modulus of elasticity. You'll remember we used modulus of elasticity in our last unit when we were talking about bending. If we didn't know what the E was for a specific material, this is how we would test it. We'd test it on one of these and find stress divided by strain to find the E. You can see it testing right here. Within this range, it'll go right back to its initial shape. And this is our formula for elongation. Delta is equal to force times length, original length, divided by cross-sectional area times modulus of elasticity. If you use this in a problem, be sure you put this part in parentheses when you put it into your calculator. That's it for this video. Please watch the next video on part 2.